Hello everyone, welcome back to 3 Deviations. In today's video, we are going to cover a few more properties of integrals. And these are going to be, again, related to those Riemann sums we were talking about earlier. So, again, the Riemann sum and the summation notation and all of that, solving with the limit, that's all the first part of integration. So even though it's a little technical, it's going to get better, and it's actually going to get better as soon as the next video. But we are going to just round off our study of this summation stuff and our elementary integral properties, and then we'll talk about more easy ways to evaluate these guys. So let's start with some integration properties. We're going to talk about the midpoint rule first. This is part of our study of Riemann sums. So if we think about Riemann sums, we had kind of three main different types of ways to approximate our area. So when we sum up all the rectangles, we could use a left-handed Riemann sum, something like this, where our rectangle touches the function on the left-hand side. Or we could use a right-hand Riemann sum where it touches on the right-hand side. And today we're going to talk about doing that when the rectangle touches the function in the middle. So these will all give different approximations. As you can see on the left, we have a little bit of room there, and then on the right, we've got a little bit of overlap. The midpoint sum is just a little bit easier to manage. It gives us a slightly better approximation. So the formula for this is pretty simple, similar to what we've seen earlier. It says the sum from I equals 1 to n of f of x bar sub I times delta x is approximately equal to the integral from a to b of f of x dx. And of course, we remember that delta x is equal to b minus a over n. And now we can make a formula to solve for x bar sub I. It's going to be equal to 1/2 times x sub I minus 1 plus x sub I. That should be pretty straightforward. We're solving for the middle of the rectangle. Let's try an example with this approximation method. So we're going to approximate the integral from 1 to 2 of 1 over x dx with 5 rectangles using the midpoint rule. We can find delta x easily by subtracting 1 from 2 and then dividing it by 5. That gives us delta x equals 1/5. And we're going to be going from the middle, so if I have my rectangle starting at 1, and that's going to end at 1 plus 1/5, so that's 1.2. Our midpoint here, so if this is 1, that's 1.2. Then our midpoint here is going to be 1.1. And then after that, we'll keep incrementing up by 0.2 until we get to 1.9. So that's what we can see here in this sum. We have 1/5 times 1 over 1.1 plus 1 over 1.3 plus 1 over 1.5 plus 1 over 1.7 plus 1 over 1.9. Of course, we need to put that under 1 because our function is 1 over x. And if we sum all of that up and then multiply it by 1/5, we're going to get something that is around 0.0692. And you can go to more decimal places. It probably depends on the calculator that you're using. But this is a reasonable approximation for what we're looking for here. All right, so now let's go over another property of integrals that we didn't go over in the last video. This is the sum of integrals rule. So this basically says that if I have a function that looks like this, so really any function, and I have my bounds a and b, and I have a new bound c, this rule basically says that this guy, which is here, plus this guy, which is here, is equal to this guy, which is all of this. So if you could imagine, if we have like a jump or a hole at C, we could find the area. We could still find the area just by separating it into separate integrals. So let's try this. This is probably a little bit more conceptual here, but let's say if the integral from 0 to 10 of f of x dx is equal to 17, and the integral from 0 to 8 of f of x dx is equal to 12, then find the integral from 8 to 10 of f of x dx. So if you remember, we are just going to be subtracting this integral here from, or we're going to be subtracting this integral here from this integral here. It's going to give us this integral here. So we already know the values of these two, so we just need to subtract them. That gives us 17 minus 12, which is going to be equal to 5, and that's equal to our integral between 8 and 10 of f of x dx. So that's a pretty easy rule. It comes in handy when we're dealing with some more complicated functions. Now let's talk about the comparison property. So the comparison property says that if f of x is greater or equal to 0 on an interval a, b, then the integral from a to b of f of x dx is going to be greater than 0. Furthermore, if I have the function f of x is greater than or equal to the function g of x on an interval a, b, then the integral from a to b of f of x dx is going to be greater than or equal to the integral from a to b of g of x dx. Final property says that if little m is less than or equal to f of x, which is less than or equal to big M on the interval ab, then little m times b minus a is going to be less than or equal to the integral from a to b of f of x dx, which will in turn be less than or equal to the integral, it's not the integral, capital M times b minus a. So this is kind of a nice comparison property. We can approximate that and set some bounds for what our integral is going to be between in a way. It's fairly helpful for us. All right, let's do an example for this. So we're going to talk about this function. So approximate the integral from 0 to 1 of e to the negative x squared dx. So what's important to know about e to the negative x squared is that it's a decreasing function on the interval that we are integrating over. So it is decreasing. So our maximum is going to be f of 0, and then our minimum is going to be f of 1. So we'll find our maximum for big M, and we'll find our minimum for little m. So decreases on the interval 0, 1. F of 0 is going to be 1. If we evaluate that, it's going to be 1. It's going to be big M. Then if we solve for f of 1, it's going to be e to the negative 1. It's going to be m, little m. So now we can kind of pinch our integral here and set it between two values. So it means that e to the negative 1 is going to be less than or equal to the integral from 0 to 1 of e to the negative x squared dx, which is going to be less than or equal to 1. What's important that we're doing here is, even though I didn't write it, we are evaluating between 0 and 1, so we're doing little m times b minus a, but in this certain case, b is 1 and a is 0, so we're just multiplying it by 1, so I didn't write that there, but that's still something that's important to remember. So now we can approximate e to the negative 1, give us 0.37 is less than or equal to the integral from 0 to 1 of e to the negative x squared dx, which is less than or equal to 1. All right, so that was our video rounding off our study of these Riemann sums and summations. First part of Unit 4 is pretty much finished. In the next video, we are going to introduce the fundamental theorem of calculus, which is going to make evaluating these integrals super duper easy. I recommend before you watch that, if you have not discussed antidifferentiation, just basic antidifferentiation, like the main derivatives that you know, just make sure that you know how to reverse that. It's video 40 in our series. So watch that just before you watch our next video, and then you should be okay, because we will be talking about antidifferentiation along with the fundamental theorem of calculus. As you will see, they are connected. Thank you for watching, and we will see you then. Bye-bye.